Hey guys, um, I'm gonna try and do a few quick videos. We didn't have a class Friday because it was a holiday, and so I'm sorry about that. So let me just try and make up for it. In terms of timing, I hope that you can watch these videos kind of after. This is when it's convenient. Hopefully before next Friday, which will actually be our next class, because Monday is a holiday too, as well. Okay, so we're talking about rings these days. So let me just remind you um, about what a principal ideal is. So we're talking about rings, ideals, and things like that. So a ring. Let me try and fix this focus. That's better. Okay, so a ring is just, for us, it means it's a commutative, meaning like xy equals yx. It has an element 1, okay, and you multiply and add things in it. An ideal is kind of like a subset of the ring, which is closed under addition and subtraction, and closed under multiplication under multiplication by the ring. So let me just remind you, R has addition, multiplication, and all the nice like usual properties. It has a 1 and a 0, and for us it satisfies xy equals yx along with all the usual like the 8 other properties of addition and multiplication. You know, things like associativity of addition and multiplication, things like that. Okay, and then an ideal, remember, and then yeah, other properties all represented by dots. An ideal is a subset of the ring, such that xy is in the ring, or xy is an element of I for all x, y, and I. I is not empty, and the other property is that Rx is in I for all R and X in the ideal, right? So you take something in the ideal, multiply by an element of the ring, and you stick inside the ideal, and that is something that you can use to make. You can turn the elements of R mod I, meaning the cosets of I. You can turn that into a ring, and we saw examples of that. Okay, so we have a few different types of ideals we want to look at. They're kind of all important in their own way. The first one is a principal ideal, and I think I've already gone through this definition in class, but I'll just go through it again. It doesn't hurt. Okay, so first of all, if A1, A2, up to AN are elements of the ring, then the ideal generated by the AIs is, we just put round brackets. Okay, it looks like a vector, but it's not. Maybe I should, maybe so I don't confuse things, I'll try and do the following notation. Put round brackets around the set of all the AIs. Okay, and what is it? Well, it's just like one way to think about it. It is the smallest ideal that contains all of the A's. In other words, it's the intersection of all the ideals, which have this as a subset, But another way to define it is just the set of sums of the form a1r1 plus a2r2 plus an rn, where r1, r2 to rn are arbitrary elements of the ring. Okay. Okay. And then we have a fact which we won't prove. This is an ideal. And it's equal to the intersection of all the ideals J which contain all the AIs. That's the intersection of all the things. So that is in what sense we mean it's the smallest ideal which contains all the AIs. That's the ideal generated by the AIs. Okay. So we might call an ideal like that a finitely generated ideal, and then if there's only one element, we call it principal. Okay, so for I equals just generated by one thing, A, in other words, the ideal generated by A is the set of all ARs such that R is in the ring. For that ideal, I is called principal. Okay, so if an ideal is just generated by one element, we call it a principal ideal. Okay. So let's see a few. I just want to at least do 2 examples. First of all, fact. Every ideal in Z is principal. Okay. And we'll talk a little bit more about that fact later, so I'm not going to prove that right now. But the idea of the proof is that you use the division algorithm. In fact, that's the crucial element. Okay. Is to use the division algorithm to prove this. Okay. You might think, well, maybe all ideals are just, maybe any kind of useful ideal you can think of is principal, but not all of them are, So let me give you a couple examples of a non-principal ideal. Okay, so another fact is that if you take R to be the polynomials with integer coefficients, and the ideal is all the polynomials f in R such that f of 0 is even, okay, then I is not a principal ideal. Okay. So in fact, it's generated by 2 elements. It's generated by the constant polynomial 2, and the polynomial x. Notice that 2 and x are both in I, because if I plug in 0 to the constant polynomial 2, I get 2, which is even. If I plug in 0 to x, I get 0, which is also even, so those are both in I. Okay. So 2 and x are both in I, and since 2 and x are both in I, that shows that the ideal generated by 2 and x is a subset of I. On the other hand, if f of x equals an x to the n plus a1x plus a0, and f of 0 is even, it just means that a0 is even. Okay, then f of x, you can write it as an even number a0 plus x times the polynomial a n x to the n minus 1 plus a2x plus a1. Okay, so in other words, this is even. This is a multiple of, so this is a multiple of 2, this is a multiple of x, so if f of 0 is even, then f of x is a combination of 2 and x. So this is an element of the ideal generated by 2 and x. Okay, which shows that I is actually contained in this. And so both, if you combine both sides, you see that I is just the ideal generated by 2 and x. Now you want to see that it's not principal. I'll say I is principal. I'll write I is generated by the polynomial f of x for some f, which is necessarily an I. Okay. Then f of 0 is even. Okay. And there's two possibilities. Okay. Right. So we are claiming that an ideal, like if this ideal is generated by one element, we'll get a contradiction. Well, to get our contradiction, we need to say, well, like 2 and x are both elements of I, so they have to be both multiples of f. Okay. Since 2 is in I, we must have that f times g equals 2. Because the ideal generated by f is all the things that are like, take f and multiply it by another polynomial. So like say g. And we're saying that 2 has to be f times some g. And for the same reason, x has to be like f times some h for some g and h in R. Okay. And now what happens, this equation tells you that f of 0 has to be 0. Well, it tells you that f of 0 times h of 0 is 0. Okay, so that is possibly useful. This tells you that f of 0 times g of 0 equals 2. Okay, what does that give you? Well, this tells you that f of 0 is not 0. This equation tells you that h of 0 is 0. Okay. Now that implies that h has a factor of x. So we can write h of x equals x times, h1 of x, and cancel the x on both sides. And then we have 1 equals f times h1. In particular, this would tell us that 1 is an element of the ideal. Well, as we'll see, if 1 is in an ideal, that implies that the ideal is the entire ring. But notice this ideal, the ideal generated by 2 and x, or the ideal where f of 0 is even, is not the entire ring, because like the constant polynomial 1, if I plug in 0, it's not an even number. Okay, so this is our contradiction. Okay, so it's not possible for I to be generated by a single polynomial. We need both of these to generate all of I. So and this was like to me, not some absurd example. This is like pretty simple example where you don't have a principal ideal. So saying that, you know, having like all ideals be principal is a pretty nice thing to have. Okay, so in general, in a ring, like some ideals might be principal, some ideals might not be principal, some ideals, might not even be finitely generated. I don't know if we'll really talk about that too much in this class. Okay, so let me stop talking about principal ideals. The next video I make will just be about prime ideals instead. Okay, thanks for watching.